While driving on a road in a car, if you make a turn, you get pushed out of the turn. This feeling of being pushed out can be annoying. There's a class of vehicles that lean into a turn while making this turn. Given the speed and a radius of a turn, can you calculate how much tilting is needed? We were tasked with making a tiltable vehicle with a small seat in it where a simulated plastic person will sit. If the vehicle makes a turn and does not tilt, the person should fall off the seat. But if you set the vehicle at the correct tilting angle while making the turn at a given speed, the person should not fall off. Starting at the source of motion for the apparatus, a DC motor has been fixed to a board. On the shaft of that motor lies a gear that is connected to a solid wooden dowel, which extends out from the motor 0.2476 meters from the center. A supporting wheel was used close to the end of the arm to keep the apparatus stable, and 4 AA batteries are tied together in series to power the motor. At the end of the arm is a metal L bracket that simulates a seat in a car. The chair can tilt 360 degrees and be fixed at a given tilt angle. There are 2 support braces that keep the simulated plastic person from falling off when the apparatus is not in motion. The angle of tilt can be calculated using dynamics. Summing up the forces results in an equation that depends on the radius, velocity, and angle of tilt. By solving for the angle, the final equation is the inverse tangent of the velocity at the seat squared divided by the radius times gravitational acceleration. The angle of tilt can be found for many different velocities, which is represented by the following graph. Since the radius is constant, changing the velocity will result in a change of needed tilt angle. As the velocity increases, the required angle increases at an exponential rate. Given an angle, you can also calculate the velocity needed so that the person doesn't slide anywhere on the seat. At an angle of 0 degrees, or when the seat is parallel to the ground, the person should fly off. As you can see, before one full rotation occurs, the simulated person falls off the vehicle. Now the angle of tilt is adjusted to about 30 degrees, and the experiment is run again. At this angle, the apparatus is not balanced and the person will fall off the seat as shown. After several trials varying the angle, we found an experimental angle that keeps the person in its seat. The apparatus spins at practically a constant angular speed. Using video frame analysis, the speed of the seat was determined to be 0.655 meters per second. Using this speed and the equation, a theoretical tilt angle was calculated. The experimental angle was 65 degrees, and the theoretical angle was 60 degrees. These 2 angles are relatively close, which proves that the mathematical model is fairly accurate. The reason why the tilt angle is required at all is because of Newton's first and second laws, which state that the sum of the forces is equivalent to the mass multiplied by its acceleration, and that an object in motion will stay in motion with the same speed and, more importantly to our experiment, the same direction, unless acted upon by an unbalanced force. The acceleration is hard to picture on the coordinate frame of the seat. Here's Ryan with a detailed description of why a person would fly off their seat if the forces are not correctly balanced.
When dealing with a dynamics problem, the first step is to set up a free body diagram with a coordinate frame. Then, you want to sum up all the forces acting on the object, which in this case, the object is the plastic person. In our case, the coordinate frame is attached or pinned to the object, therefore it is moving around in a circular motion. The forces acting upon the object are a normal force, which is perpendicular to the seat, and the weight due to gravity, which is acting in the negative z direction. The sum of the forces in the normal direction, which is towards the center of the circular path, is equal to the mass times the centripetal acceleration, AC. And AC is equal to the velocity squared divided by the radius. This apparatus has an acceleration when the angular speed is constant. The reason why there is an acceleration is because the direction of the velocity is constantly changing and tangent to the circle, and the acceleration is pointed toward the center of the circle along the normal axis. Therefore, by just looking at the magnitude of the velocity, it is clear that there is no tangential acceleration because the magnitude is constant. As a result, the only acceleration is centripetal, toward the center, because the direction of the velocity is changing. There is an acceleration of both the seat and of the plastic person. the acceleration of the seat is always equal to the velocity squared divided by the radius. For the plastic person, the acceleration is only present when there is a normal force. If the acceleration due to the normal force is not equal to the acceleration of the seat, then there will be an imbalance in forces, and the object will begin to slip on the seat. Once the plastic person leaves the seat, the only acceleration on it is gravity, which is in the negative z direction. Therefore, the velocity will still have the same direction and continue to move tangent to the circle. Although it was difficult to perfectly translate our calculations into a working model of the motion, we were successfully able to simulate the concept of a tilting vehicle whose seat angle can be adjusted to account for sharp turns. As anticipated, the object was not able to stay in place when the seat was parallel to the ground, but when we adjusted the angle to compensate, the object did not fly off. This supports the results of our calculations and proves that angle does have an effect on the motion of the object.